Okay, so this is our third video on the calculus of vectors. The first video was primarily the algebra of vector-valued functions. That carried over a little into the second. The second video is primarily differential calculus of vectors. And in this third one, we're going to be dealing with the integral calculus or antiderivative calculus of vectors. So let's go ahead and just jump right in. This is still in 10.4. Let's go ahead and let's say you were given something like this. Okay. Now, your instincts are probably wanting to change it into something like this. And in this case, your instincts would be absolutely right. Okay? And basically, that just stems from the fact that you took the derivative component by component. And it stands that you should be able to do the inverse of that, taking the integral, the antiderivative, component by component. And here is going to be a antiderivative, or a definite integral. And therefore, what we have here is we have 4 arctan of 1 minus arctan of 0, applying the first fundamental theorem of calculus. And over here we have natural log of, and when you plug in 1, you're going to get 2 minus the natural log of 1, which of course is itself 0. This winds up being pi over 4 minus 0 times 4, so that's pi I plus natural log 2j, or if you want to actually put that in component form, it'd be pi natural log 2. Okay, well that's easy enough. Well, let's go ahead and look at 43. Let's say that we are given r prime of t is t squared I plus 4t cubed j. And of course, if we want to transform that into component form, which I would because I just can't, sorry, it's supposed to be a comma, not a plus. I just can't stand unit vector form. We get that. Okay. Well, if we're given that and we are told that r of 0 is equal to j, or of course what that means is in component form 0, 1, can I take the antiderivative of this and find out what r is, like what the original function is? If I anti-differentiate and use this as sort of an initial condition, much like I did in 4.9 when I was doing antiderivatives for the first time, I can find this. Okay, but remember, I need to do a constant just like I always have. Okay, and therefore, if I anti-differentiate this, I'm going to get 1/3 t cubed, t to the 4th. But then there's a constant vector out here with both a horizontal and vertical component that is possible. It could have both. It could have neither. It could have one. It could have the other. And so I need to use this in order to figure out what that is. Now, this right here is information that was given. If I go ahead and evaluate r of 0, I wind up with 0, 0 plus c. Well, this r of 0 is the same as this r of 0, so c is obviously 0, 1. Okay? And therefore, my r of t is 1/3 t cubed t to the 4th plus 1. Now, if you want to, instead of doing it this way, if you wanted to anti-differentiate and actually put the constants inside the original components, I would just label one of them C1 and the other one C2 and do it like that, okay? And that would be just as legitimate. And then, of course, you would evaluate R of 0, and it would still wind up being C1 and C2, and then C1 and C2 would just be equal to that vector right there, okay? Easy enough. This next example is gonna take us over to 10.5. So go ahead and pause the video for a second and flip on over to 10.5 in your book. Now the instructions here, I mean, this is basically velocity and acceleration. So this section is going to have problems that are just more explicitly geared towards velocity, acceleration, all those types of cool physics stuff that Big Cat loves to ask you. So let's go ahead and start off with number 2. Okay, let's say that we're given r of t is equal to 4 cosine t, 3 sine t, and you want to evaluate at pi over 3 the velocity, the speed, and the acceleration. Ooh, speed. Okay, well, I'll tell you what, let's do velocity and acceleration first and get that out of the way, and then we'll do speed last, okay? I know that the velocity vector is always going to be r prime, okay? And therefore, it winds up being negative 4 sine t, 3 cosine t. Now, if I need to evaluate that at pi over 3, that winds up being negative 4 sine pi over 3, 3 cosine pi over 3. And because sine of pi over 3 is root 3 over 2, and cosine of pi over 3 is 1/2, that all simplifies down into negative 2 root 3 and 3/2. Cha-ching! There's our velocity vector at pi over 3. Now, I happen to also know that my acceleration vector is the first derivative of the velocity vector, or the second derivative of r. And so it winds up being negative 4 cosine t, negative 3 sine t, and then I evaluate that one as well at pi over 3, and I'm going to get negative 4 cosine pi over 3, negative 3 sine pi over 3, and that one's a little bit more messy in one component, a little bit easier in the other. It actually winds up being that. Okay, so you have the two vectors that you were looking for, but you need to remember you were also asked for speed. Speed is the absolute value of velocity. Absolute value, when you're talking about vectors, is magnitude, right? So you need to find the magnitude of this velocity vector. And remember that notation is the sort of double absolute value bars. That says magnitude. And so that is going to be equal to one component squared plus the other component squared, and you take the square root, because basically it's just Pythagorean theorem, right? And that, I'm not gonna hold out on you, I'm not going to keep you in suspense, winds up approximating to 3.775. So you've arrived at velocity and acceleration, and if you just remember that magnitude is what winds up getting the absolute value of a vector, then basically you have speed as well. Velocity, speed, acceleration. Boom, boom, boom. Okay? Now, this last problem is going to be much like the one that we did at the end of 10.4. It gives us an acceleration vector of negative 10j. It gives us a velocity initial condition of I plus j, and it gives us I guess position is the best way to describe it, of 0. Okay, well, I tell you what, I don't like any of this because it's in that unit vector form, so I'm just going to change them all into component form. Okay, now This is, again, like the ones that we did, like the anti-differentiation problems that we did in 4.9, whereas the last one that we did, we were given the first derivative and one initial condition. This one, we're given the second derivative and given two initial conditions, and so we have to march backwards twice, okay? And in this one, I'm actually going to embed the constants within the component form. I just think that that's easier in order to keep track of it. Now I know that the velocity vector is going to be the integral or the antiderivative of the acceleration vector, and that means that it goes from 0, -10, to 0 plus c1, -10t plus c2. Okay, well, if this is the case right here, I know that v of 0 is going to be c1, c2. Well, that means that c1, c2 needs to be set equal to 1, 1. That's not an issue right there. And so my v of t winds up being 1, and then 1 minus 10t. Okay, so all we did is we just took the antiderivative, allowing for the constants, solved for v of 0, found out what it meant in terms of our notation, took our initial condition, set it equal to what we solved for as v of 0, since this v of 0 and that v of 0 have to be the same, and use that to determine what my c1 and my c2 are. Okay, and so let's go ahead, and I know that r of t is going to be the integral, or the antiderivative, of v of t, which gives me t plus, and we'll go ahead and do c3 and c4, t minus 5t squared plus c4. Now, let's go ahead and evaluate r of 0. If I do r of 0, I'm going to get c3 and c4. I mean, these are both polynomials, and therefore plugging in 0 is going to get rid of every term except for the constant. And I happen to know then that c3, c4 is equal to the numerical vector that I was given for my initial condition in terms of r, and therefore basically I can sort of scratch those out and recognize the fact that r of t is simply t minus 5t squared. And that should look very familiar because it basically is the same method that we dealt with, generally speaking, in 4.9 when we were first introduced to antiderivatives. Okay, that's kind of it in terms of the calculus of vectors. There's not much more. I mean, you can get into a little bit more complicated stuff, but in terms of how fast your teacher is going through this and how much she's basically doing it by packet and hoping that you sort of have been self-taught in a lot of this, she can't really go that much more in depth than a lot of the examples that I've given to you in these couple of videos. From here, we're going to move on to polar. Again, I'm going to have to skip over the I'm basically going to have to reintroduce polar stuff to you in the midst of explaining the calculus to you, but I think a lot of it will come back rather quickly. I would consult your notes on the polar stuff as well before starting the next video. Any questions? Please do email me. Bye.